Welcome to Physics 30 Prep Fast Track. This is lesson number 8, and we're going to look at the last kinematic equation that we deal with in Physics 20. And let's take a look at it. As you have noticed from the previous 3 lessons, in kinematics we deal with 5 variables: initial, final, velocities, distance or displacement, acceleration, and time. And we'll always, in an equation, usually 4 of them are involved. We give you information that leads you to 3 of them, and then you use your equation or formula to find the 4th one, which is usually your unknown. So using the first 2 formulas that we derived, we can substitute by taking this first formula, and t here is also equal to t here. And so instead of writing t in the first equation, we write Vf minus Vi over A, substitute by multiplying it by the first part of that expression. So basically this times the second part, when we put them together and then reduce it down, we end up with Vf squared is equal to Vi squared plus 2AD. And remember, in this first equation, we don't have any mention of acceleration. In the second equation, we don't have any mention of displacement. In this equation, notice there's no mention of time, because when we substituted for time right here, we eliminated it from the equation. But it's a good equation to have. It's the 4th equation for accelerated motion. When you don't know the time, you can still figure out other components, and then once you know those other components, you might be able to go back and figure out what time is. So given that 4th kinematic expression, let's do a little bit of practice. It is critical that you do all assigned problems to gain experience with the problem-solving process. Alright, so Vf squared is equal to Vi squared plus 2AD. Sometimes this is called the quadratic kinematic expression because it contains the squares there. So a cyclist initially at rest accelerated uniformly at a rate of 2.5 meters per second squared over a distance of 20 meters. What was the final speed of the cyclist? Now this one's pretty straightforward. What you basically do is initially at rest, so what's your initial velocity? Well, it's obviously 0. Your acceleration is 2.5 over a distance of 20 meters, so basically 0 plus 2 times 2.5 is 5. 5 times 20 is 100. But of course 100 is Vf squared. And so then you take the square root of 100 and you get 10 meters per second. So try that, write it down, do your substitution, and then calculate it, and you should get, when you take the square root of 100, you will get 10. Alright, so there's your first example. Fairly simple, just substitution type of problem. Alright, another example with the same formula. A car was accelerated uniformly from 20 meters per second at a rate of 3.5 over a distance of 100. The difference between this and the first example is this time the initial velocity is not 0. It's not at rest. But you do know that it's 20 meters per second. So 20 squared, that's 400. And then times 2 times the acceleration. Acceleration is 3.5 over a distance of 100. And you will get a fairly large number. Now, what happens, of course, when you take that fairly large number and take the square root? Remember, that large number is the square of Vf. We don't want the square of Vf, we want the square root. When you take that square root, you should get something very close to 33.2 meters per second. All right? And this gives us the distance. We'd have to use a little bit of logic to figure out the direction, if direction was a factor in this problem. In this case, it's not, but it could be, and there are ways to determine the final direction. All right? One way is by drawing a picture. Very, very helpful there. And in the final example, we have a need to manipulate the formula for the unknown, in this case, d. So what we're given is enough information. We're probably given the final velocity, the initial velocity, and the acceleration but in this case we're asked how long. And of course that's the case. A skier initially at 11 meters per second, accelerated uniformly at 1.2, down a hill to a final speed of 27 meters per second. What distance did the skier travel? So therefore, as I said, we are given VF, we're given VI, we're given acceleration, but we don't know what D is. And so we have to manipulate our formula for D. The way to do that is first subtract VI squared from both sides. That gives us VF minus VI, or VF squared minus VI squared, and then we divide by 2a, and dividing by 2a, we put that down in the bottom, and we end up with D is equal to VF squared. Now that we have the, or D is equal to VF squared minus VI squared over 2a. Now that we have that, we can do our substitution. VF is 27.0, so 27.0 squared minus 11 squared, and then we divide by 2 times the acceleration, and we should get 253. A little error in the presentation here. There should be no per seconds here. It should be just meters. So a little error there. All right, 253 meters is the correct response. So down that hill, she went a distance of 253. So we've given you all of the 4 kinematic expressions, and now it's time to do a bunch of practice. One thing, though, we might want to bring into the front is what happens when you drop an object. When you drop an object, it undergoes acceleration, and it's a unique acceleration on the Earth because it's a fairly fixed number. No matter if it's a heavy object or a light object, it accelerates at a particular rate. So we should look at some examples using gravity as our acceleration.